Okay, in this tutorial, I'm going to help you understand what a chi-square test is and explain how you could use it to examine a data set and also explore some of the strengths and weaknesses of this specific statistical test. So a chi-square test is very different from the tests you may have already come across, which are are Pearson's and Spearman's, because these are tests which look for the statistical relationship between two data sets, so how correlated they are. In chi-square, we're actually looking to prove that there is or is not a statistical difference between two data sets. And there's a number of reasons we might be interested in doing that. Just to explore this in general terms, what's the difference? Let's just have a little look at a couple of population pyramids. Okay. Now, what is the data set here? Well, first of all, each age group in Germany and Uganda has been broken up into categories of 5 years. So we've got 0 to 4, 5 to 9, and all of the way up to the 100 plus. Okay. We also know the number of millions in each of these age groups. So we have a count, a raw number, the number of people for each of those age groups. Okay. Now we've got two countries. Are these population pyramids different? Well, visually looking at them, of course they are. What we can see is the classic wide base for Uganda, indicating a youthful population with very high birth rates and high death rates. So this is a country clearly at low levels of development. And here we can see Germany, which is the opposite. It's an aging population with low birth rates, relatively few numbers of children, but high numbers of older people. But are they actually statistically different? We're not looking to see if there's any kind of correlation or relationship between these two, because that's not what we'll be looking at. We're actually wanting to mathematically prove whether the population of Uganda is different from the population of Germany. Now, we can use chi-square for a number of reasons. First of all, the data has been broken down into categories, in this case, age groups. Second of all, we have a raw count, and that, in this case, it's the number of people in each of these age groups. Now, let's just go back and have a little think about applying that in general to a chi-square test. If you have two data sets and the data has been gathered in frequencies, which is the number of counts or the number you've seen in a category, then you could conduct a chi-square test. So, for example, if you walked into a classroom and you wanted to know how many girls and boys there are, well, the girls and the boys would represent the two categories, males and females, and then you would just count the number of boys, and let's say you had 10, and the number of girls, and you would have 12. So you now know the number of frequencies of each of the two genders. Okay, and they've got to be done by counting. Those are raw numbers, so how many boys? 10. How many girls? 12, rather than any kind of measurement. Okay. Second of all, and there are some key constraints here, your data must be randomly selected. So if I'm going to study the difference between boys and girls in a classroom to see if there's a mathematically significant difference in the number of girls and boys, let's say in 20 different classrooms at Morrison's Academy, I couldn't go and choose my 10, 20 classrooms, maybe picking ones that I know there are going to be more boys in, or maybe are subjects which boys are more likely to choose than girls, for example. That wouldn't be random, that would be me biasing my selection. But if I could come up with a method of randomly selecting the 20 classes and then going into each class and recording the number of boys and girls, I could mathematically then prove whether there is a statistical difference between boys and girls in different classes in Morrison's Academy, if I was interested in doing that. So that's the idea of randomness. I need to randomly ensure my data has been selected. Second of all, I cannot work with small data sets. So any category that I am using must have more than five or more, I should say, can't have less than 5 counts that fall into it. Okay. So for example, if I'm studying a river and I'm looking at rock shapes, and I've got 6 categories of rock that I'm studying. I've got very angular, angular, subangular, subrounded, rounded, and very rounded. And I've gone to a location and gathered 50 rocks. And then I've gone to a further location downstream and gathered another 50 rocks. If any of those 6 categories I just outlined had less than 5 rocks fell into the category, let's just say there were only 3 very rounded rocks in my upstream site, I would have a problem because one of my categories has got a count of less than 5. Now, there is a way around it. I could combine my categories. So I could put all of my 3 categories that were rounded, that was very rounded, rounded, sub-rounded, I could put them all together, and I could put all my angular counts together. That's my very angular, angular, and sub-angular. And that would get around the problem that one of my categories might have too small a value. Okay, so that's a little introduction to chi-square. Let's just drill a little bit deeper. How can we practically apply this? Well, let's just have a little look at this example. What have we got here? Well, we've got a result of 2 years, 1996 and 2001. And we have been measuring the amount of pollution incidents, different types of pollution incidents in those 2 years. And we are, we think by looking at the raw data that there is a mathematical difference in the, not the total number, because of course there is a difference in the total number, we can see that at the bottom, but we think that there's actually a difference in the different categories all the way through. Okay, so if I was to want to find out whether there is a difference in different types of pollution events happening between these 2 years, then I would do a chi-square. I've got categories. Here are my categories. I've got 2 differences, two columns of data that I wanted to see if there's a difference. So what do I first have to do? Well, I have to first come up always with a null hypothesis, and that is always, in this case, not that there is no significant relationship or correlation. In this time, because this is all about difference, my null always has to be there is no statistically significant evidence that there is a difference between. And then what you would do is whatever it is you're looking for the difference between. So you're saying that there isn't. And you would then conduct a result. You'd actually conduct your test and you would get a number. Okay. Now your number, you don't actually need to know the maths that has to be done to get to the number, but the number that you're looking for, we can see it here, it's 13.352. That's the result. Now that number is completely meaningless in of its own, okay? So we have to find out what that number actually means. Now this is a bit like using your critical values for the Spearman and Pearsons. The only difference is instead of a critical value and at the n, we have what's called a degree of freedom. Now, I'm not going to explain how you calculate the degrees of freedom, but we need to take that number and find out what the number of degrees of freedom we have. And in this particular example, we have 4 degrees of freedom, okay? And once we know that there are 4 degrees of freedom and we know that our result is 13.359, we need to find a critical values table to find out if that 13.39 is higher than the required critical value. Now I'm just looking for a link to that and it's not come up. So what I'm going to do is just pause for a second. Okay, so we have a result of 13.359 and we know that our degrees of freedom, which is the same as our n number in Pearson's or Spearman's test, is 4. We bring up our chi-square table. We go the D, this is the degrees of freedom. We go down to 4. And in an exam, you'd always be told this anyway. And is our number bigger than this number? Yes, it is. So we already know our probability is greater than this. So we are now 95% sure that we can reject our null hypothesis. So that's already automatically happened. When you get to this significance level, you are straight away able to reject your null. Now, we're only at 95% probability that we're correct. So can we get bigger than 13.277? Well, if we just jump back to our result, 13.359. So yes, we can. So that is, we're now 99% confident. So that's what this number here means. 0.01 means we can be 99% confident. Can we get larger than the final one? Well, no, we can't, but this would be 99.9. So normally in an exam, you don't need to test to this high level and you'd only be given these 2. So the main point we can now determine is that we are 99% confident that we can reject the null hypothesis and that therefore that suggests there is evidence that there is a difference between the pollutants in those 2 years. Okay, now let's just put all of this in the context of the questions that you're being asked to deal with. Okay, in this case, you're being asked, you've gone into a town center because you're doing urban geography, and you're looking at the number of different land uses in a town center. You've got the data for 1976, and you've now gone in the year 2020, in the year 2000, and you've found this. And you want to see if there's a difference in the different land uses found in the town center, in this case, Crieff, between these 2 years. Now, you don't need to worry about the maths, but what you can see is you've got these land uses represent your categories. You've then counted the number of shops, 17 in 1976, 20 in 2000. You observed back in 76, 13 officers were observed, 22 were observed in the year 2000. And what you're trying to do is see if there's a statistical difference between the land uses in 1976 and 2000. So has there been a change? Okay. Now, if we look at the question, it says discuss the suitability and what are the main strengths and weaknesses. Well, the main strengths have sort of already been explored in the sense that we have our data gathered in categories, and therefore it suits. Our data is counts. These are counts. This is the number of shops, number of buildings that were shops, the number of buildings that were offices. So it also meets that criteria. But all of our data here for 1976 and all of our data here for the 2000, we've got more than five or more counts in every category. So we can also do chi-square. And most critically, our data would have been randomly gathered in the sense that we recorded the land use for every building. So we're not biasing our data by selecting only some buildings and not others. If we've done the entire town center, we cannot have biased our data. Okay. Furthermore, we've got a lot of counts. We've got a very big data set. We've got 175 counts overall. So the bigger the data set, the less likely there's going to be a random result. Okay. One of the real strengths of chi-square for anything is where your data is what we call nominal data. So, for example, a shop, that's nominal data, one shop. The word shop is nominal. Okay, I have recorded a piece of data that there is a shop somewhere. And the problem with that is it's not a number. Okay, I can't give that shop a score. It is just a shop. However, if I count the number of shops in an area, I've categorized my data. I've turned my nominal data into categorized data. And I've got a number. I've got 17. I've got 13 offices. I've got 11 financial buildings. And that is where chi-square comes in. It's where your data, which is originally gathered as nominal data, is turned into categories. And then you've got the number of counts that fall into that category. Okay. So are there any weaknesses? Well, the obvious weakness is if you have data that's not randomly gathered. Another kind of weakness is the actual needing to get 5 or more counts in each of your categories. Otherwise, you can't conduct a chi-square. And the final weakness is that it's quite difficult to do the mathematics that lie behind the statistical test. So it relies on a high degree of confidence with statistics by the person conducting the test. And if you don't have that confidence, then both doing the mathematics and interpreting the results can be difficult when you do this. Great thing about this test, though, is it can be used for all kinds of different geography studies, where I looked at the population at the beginning of this little lesson. Here we've got the different types of shops. You could look at a farmer's land and see how many different types of crops he's got. He might have 7 fields of wheat and 20 fields of barley and 13 fields of maize, and that might be in 2015, and then in 2020 he might have different proportions of crops, and you could see if there's a statistical difference there. I talked a little bit about rivers and different rocks shapes found in different locations. Okay, right, that should allow you to answer these questions here, and also for question 7, when you get to this, what does 16.2 mean as a result? If that was your result for 8 degrees of freedom, well, what I would suggest you do is pay attention to 8 degrees of freedom, have a look at the critical values table, and write out, what would be your null hypothesis? Would you be accepting or rejecting it? And if you are accepting it, can you do it to the 95 or the 99?